Hi, this is probably one of the few last videos that I'll be sending to the class. This one is about the homework assignment, the one that finds the length of the shortest path. So I have to be very clear about, it is about the length of the shortest path and not about the actual shortest path, because we haven't really talked about a feature called a list in Prolog, and there's no easy way to actually spill out the path itself. Okay, there's a way to do it, because when it backtracks, we can actually do something about it, but it's not easy. So we are not spitting out the actual path, just the length of the shortest path. Okay, so if you read the instructions, all the way up to, let me pull up, this part here. Okay, so if you read the instructions all the way up to here, then we start to look into boundary. Okay, so boundary is basically limiting how much of the graph we want to explore based on the number of edges. Um, and if you pull up the assignment description along the side right now, you will see that then boundary evaluates boundary v0 v4 and 1 evaluates to false because it takes at least two edges from v0 to v4. So let's go ahead and take a look at boundary first. Okay, so we say boundary, and it has four parameters. Has got x, y as the first two as vertices. V is the source, y is the destination. N is a way for us for the subroutine. Well, I shouldn't say subroutine. Is a way for the predicate to return the actual length of a path. Okay, and then we have either B, bound, or hops H, to represent the number of hops. Okay, so the first thing that we need to do with Prolog, with most rules that need more than one, is to think about what is the base case. In other words, when is boundary going to be able to answer the question right away, whether it's true or false. Okay, so remember this symbol means only if, which means if the other side is false, okay, where the blinky cursor is, if it is false, then it is going to return false for this predicate. If it's true, then it's going to return true for this predicate. So we want to look at the base case. In other words, when can we conclusively say yes or no? Okay, so the first thing we need to do is to say, well, let's hope that h has not gone negative. In other words, we want h to be greater than or equal to 0 to begin with. So because all of these conditions are ANDed together, so that means if h is in fact less than 0, it will return false right away. It won't even bother to look at the rest of the conjunction because the conjunction is evaluated from left to right. Okay, so assuming h is greater than or equal to 0, okay, so there's always, is it 0? If it is 0, then we want to see if, but this is also the base case. So that means, we also want to see if x and y are the same, because if x and y are the same, then obviously we are done. Okay, we found the destination. Because we only got 0 hops left. We may only have 0 hops left, but we have reached the destination. So x is y is going to be okay. So now we have made use of all of these. And also in this case, n is going to be defined to be 0. Okay, so this is the part where is confusing because the first one, okay, because x and y are usually given to you when you evaluate this predicate. So when we mention x is y, it is using it as a comparison to check for equality. But in the second one, because n is usually not bound to a specific value until we get to this point. So that means the is in this case is serving more like an assignment statement. It is basically saying, hey, and you do not have any specific value bound to you, and I really have a preference to make this statement true, and the way to make it true is to say n is going to get the value of 0. So is special because greater than or equal to cannot do this. In other words, you cannot turn a greater than or equal to into something that can bind a specific value to something to a variable that is unbound, simply because there are so many values that you can bind it to, and which one are you going to choose? And Prolog does not do that. Okay, so this is the base case, which basically means x and y are the same, and x is greater than or equal to 0, which means we did not run out of hops or number of hops. So now the next one is going to be the recursive one. Okay, so we have x, y, and h again. And this time we say only if, okay, and it's perfectly okay to say that h has to be greater than 1 this time because we have to look into a single edge. And then we use the edge first. We always make use of facts before we recursively use a predicate, because if you first recursively use a predicate, then it leads to an infinite loop because it will never land on a fact first. So you always want to mention a fact first. So in the fact, we introduce a third vertex, which is z. So we say, well, there's an edge going from x to z with a particular distance of n1. Okay, so what Prolog is going to do is it will go through, it knows what x is. By the time we get to edge, x is already a bound, a variable that has a bound value. So what it would do is it's going to use that as a restriction to go down all the facts and say, well, which one is going to match the partial pattern that I'm given with. So it can only change the z and the n1 as it goes down the list to find out which one is going to match. So once we have a match here, which I think there are plenty to match with the original problem, then we can go for a recursive call. But before we go for the recursive call, we can now say that, well, hold on a second here, because h is now one, there should be one fewer hops available because we just used one for this edge. So now we say h1 is h minus 1, and because h1 is unbound, has no bound value at this point, so this is serving as an assignment statement. And then we go on and use the recursive predicate, which is to use boundary. But this time boundary, okay, let me separate everything onto different lines. Okay, so this is one thing about Prolog is, you can put everything onto one single line, you can break everything up into separate lines, but I just usually type it on the same line because I'm too lazy to press the enter key. There we go. Okay, so this time we want to go from z to the original destination, which is y, from the perspective of this current evaluation of the rule. N is still just n, okay? No, this is going to be n2, okay, because n is going to be n1 plus n2. So this is n2. n2 is basically is asking, if I give you only h1 number of hops, okay, to go from z to y, what is the distance? If it is found, what is the distance of a path from z to y? And then one last thing is to now relate n1, n2, and n. So n is going to be n1, which is the edge going from x to z, plus n2, which is the path, the length of the path from z to y. Now, which path are we talking about? Are we talking about the shortest path? No, we are talking about any path. Okay, and that's why there are multiple answers in this case. So the whole purpose of boundary is simply to say, well, if I give you a limitation of how many hops we can go, can we find a path from one particular vertex to another vertex? So with this type of because of h1, is always h minus 1, and this is the recursive part. So that means boundary cannot be endless. It has to end at some point. Now, if it fails, okay, if I try to find a path that does not exist, what's going to happen is eventually everything will fail with h is greater than or equal to 0 for sure, okay? And it is also possible that we cannot even find an edge, between the two vertices that we are talking about. In which case, Prolog has an automatic mechanism to backtrack. Okay, so when it backtracks, it simply means that it will go back to an earlier point and see if it can make that true. So if boundary fails, it will go back and then go back, and it will try to say, well, can I find another edge to make this predicate true, and then go forward again. So it automatically perform what we call a depth first search, um, without you having to specify that you want to do a depth first search. So that's one really cool thing about Prolog, is it will automatically backtrack and do the depth first search to find all the solutions. So at this point, we can at least give it a try, right? So we'll give it a try and we'll say, okay, let's look at boundary. And we can go for the base case. Okay, so we say, we want to go from v0 to v0. Tell me what the length is, and I'll give you 10 hops. Okay, and press Control Enter, and it complains about arithmetic v0/0 is not a function. It's complaining about line 10. Well, in that case, we can say xx. Okay, then we don't need the comparison. Although I don't really fully understand why it complains about that. Because both of these are bound already. Alright, so this time it does say 0. Okay. So I cannot compare two bound variables for equality if they're both coming from the left-hand side. Alright, well, now that we know that. Alright, so this works. So now we go for another case where there's only one single edge. So we say, what about v0 to v5? Okay, so v0 to v5 is an easy one because the first edge is going to say, yep, we can definitely go from v0 to v5, and the distance of that edge is 3. So, but it forces the predicate evaluation to go for the second one. So we want to see if that works. Okay, so we press Control Enter, and it says it's 3. And we can always click stop here, because otherwise it complains about things later. It also finds 5. Now the reason why it finds 5 is because there's a loop. So this loop has to go from, the problem is it doesn't tell me which loop it has gone for. So I think it's gone for this loop here, v0 to v2 with a distance of 1, v2 back to v0 with a distance of 1, then it goes from v0 to v5 with a distance of 3. So I think that's where it went. And there are multiple answers too. So basically, because we've only specified the number of hops, so it can go for loops. It can revisit the same vertex or even the same edge, more than once. But that's okay. Okay, this is okay because we'll fix this problem later. But the key is boundary. Given a certain number for hops, it will find out the answer. Now we can also try to test again this time, with the number of hops specified as a 0, because this should be false, right? Because we cannot go from v0 to v5 without a single hop. So Control Enter, and it returns false. Okay, so that means we have now tested these two rules for boundary, at least to the point that we know that it seems to work. So now we will move on and move on to the next predicate, which so in the notes or in the assignment description, it says once boundary is implemented, the next predicate to implement is find boundary. X is the start vertex, Y is the destination, N is the length, and interestingly, H is also the number of hops. But the intended use of find boundary is to bind X and Y to the start and destination vertices, N remains unbound, and H is bound to 0 in the query. So in the query here, we want to use bound as a 0, and then I further explained in the homework description that says because find boundary is a loop, if h equals to 1 does not find a path, then we'll try h being larger and larger and larger. Okay, so let's go ahead and take a look at find boundary. Okay, so we got x, y, and basically serving the same purpose as before, but h this time is start with a 0 instead of decrementing. Okay, instead of decrementing like here, okay, it is now going to be incrementing. Okay, so we'll use h here, and once again we have to think about the base case. So the base case is x and y are in fact the same, so we say they are the same. So that means we specify just x over here to specify they are the same. If you use an edge as the base case, that's fine too, okay? Because the only difference of whether you want to handle the case when when the start and the destination vertices are the same, or whether to specify that you have x, y, but there's an edge between x and y with the base case, is the assumption of whether the start and the destination vertices can be the same or not. So since I did not specify that in the homework assignment, it's okay to use an edge as the base case. So in this case, there's no restrictions whatsoever. So I just want to say that n is 0. Okay, it doesn't cost me anything. There's no distance going from vertex x to vertex x, and h can be whatever it wants. Okay, h in this case can be whatever number that h is going to be. There's no restriction for h, and I think it complains about it. I have to turn it into an underscore to basically say not care. So we have another find boundary here. This time it is going to be recursive. Okay, so once again we have the 4 parameters. And the first thing we want to evaluate, because it won't evaluate the second one if the first one succeeds. So by the time we get to the second rule, that means the first rule has already failed, which means we do not have the source and the destination vertices being the same. So we know they are different. So since they are different, we can now say, let's see if we can find an edge between those two. So we find an edge between x, z. Okay, so z is a new vertex, and we have n1 here. Okay, so we have an edge going from x to z, and then eventually we want to say find boundary zy. Okay, and just like the other one, n2 and x1. Okay, because the number of hops would have changed. There we go. All right, so this is so this time we want to think a little bit more, okay, and the next one is n is n1 plus n2. So even this part we can copy because we want to find what is the length of a path in h hops, right? In a certain number of hops from vertex x to vertex y. So the difference this time is how does h1 and h relate? Because we want to find the number of hops. So h is not going to be bound to begin with. H is going to be unbound. So that means over here we also have to say now h is 0 because it doesn't take us any hops to go from a vertex to itself. So this means by the time we get here, h1 also has a specific value because we're coming back from a successful evaluation of find boundary. So h1 has a particular value. H is unbound, so we want to say h is h1 plus 1 because this is the number of hops in order to go from x to y using the recursive definition. All right, so this time there are 2 unbound values to begin with. We want to find out how many hops, and we also want to find out what is the length of the shortest path. So when we ask the query, we ask find boundary. So we have, let's try the base case again. Okay, v0, v0, n, and h. Okay, press Control Enter, and it evaluates the first time, and it says h is n is 0. So it's basically saying both are zeros in this case, which is correct. Okay, so they're both zeros in this case, and we can stop now. Now we can also find between two different vertices, so v0 and say v4. Okay, and it says it will take at least 2 hops for a path that has a distance of 6. Now obviously this is not the shortest path, because we know the shortest path only has a length of 3. Okay, but it is nonetheless a path, so we know the shortest path cannot have a length that is greater than 6. Okay, it's at the worst, this is the length of the shortest path, but it may not be the shortest path either. We just know that there is a path between v0 and v4, and it only takes 2 hops, okay, to get there. Okay, so if you read the homework assignment, it's a little bit different compared to what we have here. So it basically says that if one does not find a path, then we increase the number of hops to 2 and 3 and 4, and find boundary is supposed to use boundary. So I actually implemented this incorrectly. Okay, fine. So we'll take this out, okay, because I want to be consistent. I got the same thing done, okay, but without using boundary. But let's go ahead and use boundary within find boundary, okay, because I want to do the homework assignment as you do. Okay, so now we ask, how do we do this? Because h is bound to be 0 to begin with, so we start with, okay, let's try 0 first. Okay, if it doesn't work, then we go ahead and try something with a higher value, with a larger number, okay, with h. All right, so the way we do this is to say we use a not here. So we specify a not here to basically say if there is no path, okay, with the current number of hops, okay, which is n h here, then we're going to do something. Okay, then we say h1 is h plus 1, so we add 1 to the number of hops available, and then we use find boundary again. So then we say find boundary x, y, n, and then with h1 this time. So it is it's recursive, and in this case I don't even think that we need the first rule also has to be changed, because it's no longer specifying, because boundary is the one that takes care of business. So this one also needs to be changed. It only needs to say boundary x, y, and h. There we go. Okay, so let me explain this again. All right. So because h is always bound to a particular value based on the description in the homework, so h always has a number. So if there is a path within h number of hops between x and y, then find boundary would just kind of return and go like, yep, I found my answer, okay, based on a given number of hops, there is a path, and it returns true. Now if that is not true, which means which means boundary is false, then it goes to the second rule, and obviously we don't need this anymore, because it's going to reevaluate the same thing. So now we can say let's just add 1 to the number of hops that is given to me, because I won't execute from the perspective of this particular rule. This rule is not going to evaluate unless the first rule fails. If the first rule fails, we already know that there is no path between x and y within x number of hops. So then we increase the number of hops by 1, and then we use find boundary again to engage the first rule again. And this time the number of hops is increased by 1. All right, so let's check whether this works. Okay, so we will ask find boundary v0 v4, and we specify and here, and we put a 0 here, which basically means um, start with 0 hops, which means the first rule is going to fail, but then it will move on to the second rule. Okay, and then x is increased by 1. Then it will try to see if I can find a path within 1 hop away from v0 to v4. That will fail as well. Then it will increase again. Okay, so press Control Enter, and it complains about singleton. Oh, okay, because I've used a y here, and y really needs to be here too. Okay, that was my bad. And let's try to reevaluate this. There we go. So it returns a 6. Okay, in other words, it doesn't we are not going to specify the number of hops in this case, because it's automatically incrementing the number of hops by itself, and then within within a particular number of hops, it will try to find a path between the start and the end vertex. So it's basically expanding. Okay, so this is there's a particular name for this type of algorithm, and I want to find out exactly what that name is. So let me do a search here so you can see my search. It's called successive. Well, let's just look for successive path, shortest path algorithm. The successive shortest path algorithm searches for the maximum flow, optimizes the objective function simultaneously. Max flow, okay, that's not exactly what I intend to find, but it's close. Basically, it's doing a depth first search. Okay, so if I go back to the algorithm, which is this one, it's basically doing depth first search, but the depth is limited. Okay, the depth is limited by the number of hops. So that means we are doing a depth first search with a search radius of 0 to begin with. Okay, and that will only succeed if we are trying to find if the source and the destination vertices are the same. Okay, so if we say source and destination are the same, then if the first one would succeed, because we already know that boundary xx and h will succeed. But for anything else, it's not going to succeed, because you have to have at least one edge between a vertex and a different vertex. So then it will increase the search radius, okay, so to speak, search radius in terms of hops by 1. So now we are saying, okay, let's start from the start vertex and explore everything within 1 hop away. Okay, if I cannot find a destination this way, okay, let's increase the number of hops to 2. So now we have a search radius of 2 hops away, then 3 hops away, then 4 hops away, and 5 hops away. So the idea is, using this particular method, I don't need to worry about loops in the graph, because even though loops would introduce inefficiency into the algorithm, because it will go for the loop, but it will only go around the loop so many times, because the search radius is limited. So each time we go through a loop, it's going to consume hops, and eventually we'll have no hops left, and the loop has to, the exploration of the loop has to end because of that. So this is a rather tricky way to handle the case when we do not have a mechanism to detect that we have visited a vertex already in a search. Okay, so find boundary is working now. So we want to go back to v1 to v4, press Control Enter, and you can see that it can generate a whole bunch of answers like that. And that's because it just keeps going on and on and on. It just keeps increasing h1, to a larger and larger value, because remember, it even if it finds a solution, it backtracks and it asks, well, is there a different way to do it? Okay, then it backtracks again and then asks, is there a different way to do it? So the number of n keeps going up and up and up as a result of that. Okay, so you can see, the more you go, like this, it does go back to 3 occasionally. Um, Not quite sure why it can go back to 3 eventually, but most of the time it should be increasing, because what's happening is it is increasing the number of hops in order to search different paths. And I do not have 2 edges of 0 cost, so it really should not go back to 3. There's only one path with a cost of 3, so I'm going to have to look into that. So let's stop here. Alright, so after find boundary, then we can have a shortest path, which is already given to you, and it needs to use a path bound. Okay, so that means, let's go ahead and implement path bound first. Path bound. So this time is bound by the length of the path. It's not bound by the number of hops anymore. So let's go read that portion. So the predicate path bound x, y, and l is intended to be used with x and y bound to the start and end vertices or destination vertices, and is unbound to receive the length of a path, but it has to be shorter than the bound variable l. So the length of the path has to be less than l in order to qualify as, yep, we found another path, but it has to be less than the length limit l. Okay, so let's look at bound path. So once again, we want to handle the base case first, which is xx. Okay, we are already on that vertex. The start and the destination are the same. We don't know what is the length of this path, but we know what the limit is. Okay, so in this case, the first thing we need to make sure is L is greater than or equal to 0. It cannot be negative. Okay, because otherwise it can keep going. As long as L can be negative, it can be endless. So we have to make sure that L is non-negative. But as long as L is non-negative, we have met all the requirements. We are already there. So that means n in this case can be 0, because we have found our destination, and the path of going from the source to the destination in this limited case is 0. And we also are successful because the length limit is greater than or equal to 0. So we have met all the requirements, and then path bound is going to return true. So let's go check this first. Okay, let's check the base case and make sure that it does work. Okay, so we say path bound v0 v0 itself, and we say give me the length of this path, and I'll give you a limit of 0, which is as low as it gets, unless you want to go negative. And it says n is 0. Okay, that seems to make sense. But if you give it a negative length, like -1, then it should return false, because that would not have met the first requirement. Okay, that's good too. If you give it like 10, obviously that's fine too, because any number that is greater than or equal to 0 will make this true, right? Okay, so that's all good. But if you ask it to go find a path from v0 to v4 with 10 as a length limit, it's gonna fail because it does not have the recursive part yet. Okay, so now we can move on to the recursive one, which is how we kind of implement loops in Prolog. All right, so in the recursive case, what are we gonna do? Well, the first thing is we still want L to be greater than or equal to something, but since it fails the first one, you can always say that too. Okay, you can always specify L is greater than or equal to 0, which means if L is negative at this point, it's going to fail. Okay, so that's fine. Then we want to find an edge. Okay, so the difference between the base case and this one is this one tries to use a fact as a step, quote unquote step. It's kind of like the step of proof by induction. Okay, this is where we quote unquote increment the case by 1. So we want to find an edge between x and z, and the distance of that edge, we'll call it n1. Okay, and now we have to say, well, if we have used up n1 out of L, okay, that means the new L for the recursive use of the predicate is going to be L minus n1. So we say L1 is L minus n1. This is the new length limit. Then we can recursively ask, is there a path, okay, between vertex z this time and vertex y? I want you to tell me what the length is. Let's call it n2. But the length limit is no longer L. Instead, it is L1 because we have just used up n1 of L for the edge from x to z. Okay. So if path bound returns true, which means, yep, I found a path with length n2 between z and y, and it meets the requirement of being less than L1, then we can add those two together, those two being n1 and n2. So n is now n1 plus n2, and that concludes this particular rule. So we want to give it a try, right? So the first thing to try out with this one is put a 0 here. Okay, if I put a 0 here, it's going to fail the first rule because this will only match if x and if v0 and v4 are the same, but they are not. So the second rule says L is greater than or equal to 0. Initially, that is true. Okay, it's all good. Then we want to find a third vertex that v0 goes to. There's plenty to choose from. Okay, if you go to the beginning of this program, there's plenty to choose from, which is good. Okay, so let's pick a v5. Okay, so we pick v5, and so n1 is, I cannot remember the actual length. I can look up my notes here. Okay, so it's 3. Length is 0, so L1 is going to be -3 because path bound is always going to return false if the limit is already less than 0. So it's going to return a 0. So this particular predicate will be false, which is forcing the engine to go back to look for another option. L1 doesn't have another option because it is based on L minus n1, but edge has another option. There are other vertices that v0 can go to. V0 can reach other vertices using a single edge. So it's going to go back to the facts, okay, all the edges, and find another edge that can meet this condition. But since no edge has a distance of 0, so that means no matter which edge is choosing, L1 is going to go negative by the time we get to path bound, and as a result, this is going to return false because there are no paths bound by 0. Okay. So what about 1? Okay, can we find a path that has a length that is less than 1? Okay, no. What about 2? No. What about 3? The answer is yep, we found at least 1. Okay. The interesting thing, which I kind of have to evaluate, is there's only one path in this case, so that is correct. Okay, this is good. It doesn't find any other path. It finds only one path with a length of 3. Okay, so now we want to combine the two. Okay, so in the notes I said just copy this, right? Shortest path x, y, n. Okay, only if, okay, oops, only if, and the next one is find boundary x, y, and 0. Okay, So the change back that I made earlier, because I found I had the first implementation of find boundary, and then I have this one here. It is necessary because otherwise, this won't work. If you use the shortest path rule that I gave you. So this part basically just means, okay, I want to find the length of the shortest path from x to y. The first thing I want to do is to just to say, okay, let's keep expanding the search radius until we actually find a path, not necessarily the shortest one, but a path from x to y, and tell me what is the length of that path. Okay, so that length is definitely not necessarily the best, okay, but it does give us a upper limit, right? Because the length of the shortest path between x and y cannot be more than n. So now we say and backslash plus is a not, it's negation. And we talked about negation in class, okay, when we talked about the Jedi example, okay, being Seth tolerant, we need to use negation. So this negation is making use of path bound x, y underscore n. The underscore is necessary because otherwise Prolog will complain that we have a singleton variable, because if I specify another name here, okay, if I specify, let's say m over here, this m is not used for anything else, and Prolog does not like that. So we use the underscore here to make it happy. All right, so what does that mean? That means the first call is finding the length of a path between x and y. The second call, or the second part, is not a single call because it basically is asking, there does not exist, okay, it is not the case, okay, it does not exist a path from x to y that has a length that is less than n. So if the negation of path bound is true, okay, then the entire predicate is true. Okay, we found the length of a path from x to y, and there's no path with a shorter length. Then we have found the length of the shortest path by definition, right? So now the question is, oh, but Tech, this is not going to work because, okay, find boundary x, y, and 0. Oops. And remember, x is v0 and y is v4, okay? And then we press Control Enter, and it says 6, okay? Tech, there are plenty of paths, okay, with a length of less than 6, okay? In other words, if I plug that in and say path, oh, I cannot use multiple queries on the same, in this interactive box here, but I can say path bound, okay, v0, v4, and put a 6 over here, Control Enter, and path bound, oh, I need one more variable, okay, underscore 6, Control Enter, and it says true. Oh, okay, well, if this is true, this is negation. Doesn't that mean that the negated path bound is going to be false? The answer is true. Yes, you're absolutely right. Okay, 6 is not the lowest one. So what's going to happen in that case is this negated predicate is false. Then it goes back to the first predicate and say, Prolog engine, give me another solution for this guy. So the Prolog engine will know where it left off last time. Okay, in other words, it knew, how find boundary, which over here has found, the how it finds the first path. So it remembers that. So when it backtracks back to this point, it's not going to give us the same path again. It will give us a different path, and then a different path, and a different path. Now, the way we can kind of visualize that process is to just type, find boundary x, y, okay, v0, v4, and 0 over here, and then press Control Enter. You can see the first one it finds is 6, which is not gonna is not going to work because there are paths with a length that is less than 6. So when it retracts, then it's the same thing as going for next. Okay, so it finds a path with a length of 5 from find boundary, and then path bound says I can find a path that beats that. Okay, so now we go back to find boundary again, right? And the third time it says, okay, I'm not going to revisit the paths that I have already visited, but this time, I found another path of a length that is 3. So this time, oh, okay, I think I know why found boundary can return 3 multiple times, but we'll get through this first. So, but this time, when I plug that number in to path bound, okay, let's check this out. Path bound v0 v4 underscore, and this time it is a 3, right? Control enter. Fine. All right, let's try it again. Then it says true. Okay. Nah, that should not be true, should it? All right, so let me check. Aha. Okay. So the problem has to be here. So path bound should return false if L is okay. So let's go back to this path bound first. Okay, so because this query should have returned false. Okay, and the reason why it returned true has to do with how we check, whether L is satisfactory or not. So in this particular path bound, if L is 0 at this point, then we have failed. In other words, if we ever get to this point, path bound would have failed already, which also means back to here. There are 2 ways to fix the problem, but I just want to find out what is the best way to fix the problem. I cannot turn this, into because okay, so let's look at this case here. Let me explain why it is returning true, but it should be returning false. There really is a path from 0 to v0 to v4 with a length of 3. So if you look up the homework assignment, that path is going to be, let's see, through v3. So v0 to v3 is 2, v3 to v4 has a distance of 1. So that path would have met it would have a length of 3. But we are looking for a path with a length that is less than 3 in this case. So that is the problem. So if we follow the algorithm, the first time it evaluates, L is 3, 3 is greater than or equal to 0 is true, we are all good. There's an edge from v0 to v3 with a distance of 2. So now 1 is L minus, is 1, okay, 1 is the result of 3 minus 2. So we call path bound again. This time we are asking from v3 to v4, is there a path? And the limit of that path in terms of distance is 1. So that is still correct. And report back the actual length. Okay, so then we go back here, it's going to fail this condition. It goes back to this condition here. When it gets back to this condition, we have a problem because L is greater than or equal to 0 is still true. We find the edge. So the way to fix this problem, is to change, well, one way to fix the problem is to change it here so that we enforce that because if it gets down to 0 at this point, if L is, I mean, excuse me, if L1 is 0 or less than 0 at this point, we can basically say we are done. Okay, we're just going to return false. There's no need to call path bound again, which means this condition is never going to be useful. Okay, so we can refine the condition here. So we now have to say that L1 has to be greater than 0. Cannot be 0 itself, but it has to be greater than 0. Because if it is 0, that means, the best we can do is to find a path, a length that is matching, but we want something that is going to beat the distance at this point. So L1 has to be greater than 0 in order for this path bound to have a chance of succeeding, which basically also means this is always going to be fail. This is basically useless. So we found the second edge, and that is going to fail. So we still need, okay, alrighty. I already had the solution in my answer. I was just trying out a different way to do it by not using an edge in the base case. So in this one, there's no way for us to avoid a base case that makes use of an edge. With the other two, yes, but with the other one, we cannot. So with this one, we have to say that L is greater than 0, cannot be. Actually, we can go for edge first. So we find an edge between x and y with a distance of d. And then we have to say that d has to be less than L, not less than or equal to, has to be less than. And if that requirement is met, then we can say n is d. That would solve the problem. There we go. Okay, so let's go back here and try again. This time it should fail, it should return a false. And that is exactly what we want, because we want, there's no path with a length of less than 3 at this point. So with this out of the way, with path bound implemented correctly now, then we can find boundary. So we ask find boundary. Nope, not find boundary, shortest path, the last one. So now we can actually evaluate shortest path. V0, V4, N, control enter, and it finds 3. Okay, so if you ask for the next 10, they're all 3s, okay? So now why is it returning all 3s? The problem has to do with find boundary. Because find boundary, after exhausting everything within 2 hops, which is the first 3, where the first 3 is coming from, it's going to go like, we can increase h1 again, increase the number of hops, and it will find another path again, because when you increase the search radius to 3, 4, 5, 6, and so on, any path that is within a search radius of 2 will still be found. And that's why we keep finding the path of a length of 3. It's because when find boundary has already found 1, okay, which is this guy here, it still wants to backtrack, because, okay, so the first call is going to find boundary is going to be true, so the whole thing is going to return. But then when we ask for other answers, it will then try to call boundary again, and then it will find it is no longer true. Then it's going to go for the false case here and keep increasing h to increase the search perimeter. So we have to basically, if we don't want these repetitive answer, because this will keep on going forever, because as we increase the search radius, it will just keep finding the shortest path again and again and again, so it won't stop. So if you just look for the first answer, which is already correct, okay, then shortest path is working already. On the other hand, if you say I don't want it to keep doing stuff like this because it doesn't make sense, okay, it's just a waste of processing resources, it should have just returned a 3 and conclusively say that that is the answer. Okay, do not ask me any further. Okay, that's the correct way to specify that. So we wanted to be able to search for everything, but as soon as it finds one, we want it to stop and not to reevaluate. So we need a cut operator. But we don't want to cut it too fast, because if we cut it too early, then it won't find within the same search radius other um, links within the search radius. So alright, so this is probably something that I want to do on a different day, but as far as the homework is concerned, this is the solution. So I'm going to save this and send it to all of you so that you have a copy of this too.